Right, so Andreas will make the presentation of Artem. So Andreas has been involved in Luster development since its inception, from early prototypes in 2000 through several companies over the past 20 years. Andreas has been one of the lead Luster developers. In 2012, he took over the role of Luster Principal Architect, and since 2010, he's Luster CTO at OneCloud DDN.
Thank you. So I'm presenting on behalf of Artem, who's a longtime Luster developer. He's mostly focused on LDISKFS and E2FS progs, but has contributed to other areas of Luster as well. So today's presentation is about improvements to LDISKFS, and in particular focusing on the multi-block allocator. This is particularly important today as the size of OSTs is growing quite large. We're regularly seeing OSTs in the 500 terabyte range and growing up to be 1 petabyte in some cases or more. And from my point of view, the first Luster file systems were under a petabyte, and so to have 1 OST, that's pretty amazing. So the multi-block allocator is was developed at Cluster File Systems many years ago, and its goal is to efficiently allocate large chunks of disk rather than the old allocator would allocate 1 block at a time, and multi-block allocator obviously allocates multiple blocks, and it's used for larger I/O sizes, and it works essentially by a multi-stage selection process. First, it locates a suitable group in the file system, and with these large file systems, a petabyte OST has 8 million allocation groups, and so first it has to find an allocation group, and then it has, it's called a buddy bitmap. It's a power of 2 bitmap that allows you to efficiently, just through bit scanning, find the largest free chunks of space in the disk, in that group. And so, as all things, it's supposed to be, newer things are always better, but in fact, we've been seeing as the OST size grows, we do have some issues with the allocator in LDISKFS. We've seen that, with large OST sizes or fragmented file systems, we can have high latency for block allocation, and the other problem is that it has sort of a round-robin nature. Like, we try to, not use allocation groups for a long time so that they can get the maximum amount of blocks freed out of the group. But with spinning disks, you find that at the end of the disk, the physics dictates that the higher block addresses are closer to the center of the disk, and so the linear velocity at the inside of the disk is lower and lower bandwidth. And upstream has been doing some work on ext4 MB-alloc as well, but it also had some problems, and so both of them need some development effort. And so the basic idea behind MB-alloc is that it's in the left side you can see we tried to allocate from the free parts of the disk, and this works good while the disk is relatively empty. The allocation window, we do forward scanning, and so that works while the disk is relatively unfragmented. But as time goes on, you get free space fragmentation, and then it has to do a lot more work to find the free space. And so, in fact, with 8 million groups, it's not just a matter of doing the in-memory scan, reading off the bitmaps and things from the disks is 8 million IOPS, and at 100 or 200 IOPS per second, that's can be 10 minutes after a mount to read all of these groups, so that can take too long. So there's a few mechanisms that we have at our disposal today to improve that. One is there's an interface pre-alloc table that, well, there's two things. One is there's a proc interface MB groups that dumps the buddy bitmap that can tell you what the distribution of free space is and how big the free space is in each group. And so that table can be very long, 8 million lines, but it can be processed in user space and then use it to tune group selection so that you don't spend time looking for groups with lots of free space when in fact there aren't groups that have 16 megabyte free chunks anymore. And so this needs active participation from a user space tuning, and doesn't always work. The way that MBAlloc works today is essentially 4 passes, right? The first pass, criteria 0, means it looks, for the optimal allocation case. I mean, Lustre is already doing the write back caching on the client, and so we do have fairly good I/O aggregation if the applications are well behaved. And so, RPC size can be 4 or 16 megabytes up to 32 megabytes. And so when we send the large RPCs from the client, they're aligned, to the logical offset of the file in 4 megabyte multiples, for instance. And so that works well with aligning those to the disk. And so in the first pass, we tried to find aligned chunks of free space that will also align like with RAID stripes and things in the underlying storage. And if the CR0 pass doesn't find anything, we go to CR1. It tries to find a group that has an average free space of, let's say, 4 megabytes. And so that would mean there'll be some spaces, some groups that have more than 4 megabyte free chunks, and so those are suitable. But again, if it does a pass with CR1, it doesn't find any groups. It just tries to find any group that has enough free space. And finally, if that fails in CR3, it will fragment the allocation among multiple groups and just use small free space. And so this is a problem as file systems get 80 or 90% full. There aren't very easy choices for finding allocation space. And so, maybe in Lustre 2.12 or 13, there was essentially a patch added to allow a skip threshold so that, instead of looping over, all 4 million groups in a file system or 8 million, it says, it's unlikely for me to find, an excellent allocation quickly, so I'm just going to skip the first loop and start looking right away for a group that has an average free space. It'll start at the CR1 loop and try and find an average free space in a group and then do the allocation within there. So you would know that if the average free chunk size is at least 4 megabytes, there has to be somewhere in that group a chunk that is 4 megabytes or more. And similarly, let's say after, if there's only 15% of free space left, it'll go directly into the CR2 loop, etc. And so, this avoids a lot of in-memory scanning and speeds up the allocation at the cost of, not having as good a allocation choices. And so one of the problems that we found was that, this is great for testing, but there isn't a persistent way to set it. I mean, so we added in a mount option, and there isn't a tunable parameter, but we would like, to use the normal Lustre set param and set param minus p to be able to tune that. So we had to add, or we haven't done this work yet, but we want to add in the ability to tune parameters under the LDISKFS, SysFS, LDISKFS, and ProcFS. Because currently we just look in ProcFS luster and SysFS luster for tunable parameters. But that should be relatively easily done. And so you can see for this tunings here for the C1, C2, C3 thresholds, you can see when that is needed, right? By there's the MB stats, the multi-block statistics. You can see that, in the left case, it has this counter useless loops counter. And so in the right case, you can see, these thresholds were tuned too low, and 4% free space, 1% free space. And so what happened was, the allocator is spending a lot of time, looking for free space with criteria that can't be matched by the file system. And so, you see these 1 million, 2 million count of useless loops. And so, those thresholds have to be adjusted higher so that, it's spending its time effectively finding free space. The other issue that is, causing problems with, especially with these large disks, is, allocating space at the end of the file system. So we have this MB last group counter, and so that records the previous group that was used for allocation. And so this round robins, just increases until it hits the end of the disk and starts at the beginning. And so the reasoning behind that was that, if you're allocating in a forward direction, it's fairly efficient, and then that gives the maximum time for the files behind the MB last group to free up space in the file system. And so that's good, but as you can see, there's this large range of blocks that have been freed at the beginning of the disk, and those can be 20 or 30% higher bandwidth, and so that's pretty significant compared to the last part of the disk. And so what we would like to do is reset the counter to the beginning, but only when there's space that's freed, right? Otherwise, if we're always allocating at the beginning of the disk, then we're spending a lot of time rescanning the full part of the beginning of the disk. So you can do this manually, but it's not, just write 0 into this MB last group counter, but that's not something that happens in production. That's, more of a benchmarking kind of thing to do. And so, you can have a user space script that monitors free space again, but that's not, very automatic. There's lots of things you can do, but people don't because they don't know they need to do it. And so it's more important to get it done automatically. And so there is some work being done. I think it comes up in a later slide, this LU14438. It's a patch that's been proposed by HPE to do that. So, as I mentioned earlier, one of the problems with so many metadata groups for allocation is that the mount time can be very long, right? So if you have 8 million groups, we did have a problem. As soon as an OST mounts, it contacts the MGS to get a new configuration log, and then the first thing it tries to do is, allocate, 64K or whatever of space to try and write out the new configuration log. And so it was scanning, every single group, using this CR0 criteria. It took, reading all of these bitmaps can take 10 minutes, right? And so that, hurt your mounting time significantly. And so, we've put in special cases to avoid, trying to find a perfect allocation when you're doing a small small allocation like that to speed up the mount time. But again, that's kind of a hack. So essentially what we've done is if you're mounting up the file system and you haven't read all of those groups, then don't bother trying to read all of them from disk. Just try to find, one group that's good enough and has some free space, and then allocate immediately from whatever's been loaded into memory. And then we have essentially a background thread that runs after mount, and it goes ahead and prefetches all of the bitmaps from disk. And so that doesn't delay the mount, but eventually we'll read the metadata into memory so that it can be used for allocations afterwards. And so this, there's a new allocation heuristic that's being worked on by HPE that's trying to bias allocations towards the start of the disk to avoid, using the slow end of the disk if that isn't needed. And so this is still in development, but there's discussions going on about this to, they have essentially trying to balance between, trying to do all of the allocations at the beginning. So if they have this KLTA rate, and they said, in theory, if KLTA rate is 100, it means that the beginning of the disk has to be 100% full before we start allocating, after the start of the disk. And so that's, not a reasonable parameter, but it's just shown here for illustration purposes. The default rate at 25 means that, if the beginning of the disk is 25% full, then it can extend out the allocation region, and so it has a sum of a balance between keeping allocations at the start of the disk or using the later parts of the disk. And so in the example here, the file system is 22% full. They have this KLTA rate of 25, and so it means that when it's 25% full or less, then if you've scanned, to the MB last group has hit, 88% full, right? So that's 22% of the file system divided by the rate. It will reset to the beginning and try and prefer allocations from the beginning of the disk. And then because, performance is not a linear function of the offset in the disk, they have a KLTA start parameter that says, the beginning, whatever fraction of the disk, 10%, is considered to have linear performance, and only the end of the disk has a declining performance. And so you can bias it so that it the beginning of the disk is treated equally well. And so we still have discussions on this. It's not quite sure what the right parameters are, but it's one option. The other thing, in the upstream ext4, they have done some work for this MB optimized scan, which is, instead of doing a linear scan across the disk, they've introduced an array of free order blocks, right? So that they have an array of 128 meg chunks, 8 meg chunks, 4 meg chunks, 2, 1, all the way up. So if you're looking, and as an allocator, you're looking for an 8 megabyte chunk of free disk, you can do an order 1 lookup in this table to find a group that has 8 megabyte free block. And so that's very efficient. And then they also have a separate RB tree that they use for searching in CR1 so that you can find average free groups. It turns out that the RB tree has a bit too high of overhead. And so what they're doing in the patch that hasn't landed yet in the upstream kernel. They're replacing the red-black tree with another array. And so that will also give order 1 group selection. And so this is good, but it doesn't solve the problem of beginning versus end of disk. And so we do need to do something in that area. What we can do is try and bias allocations towards the start of the disk in the lists, so that we can put, currently it has a bug that it inserts the entries in reverse order, so it actually biases everything to the end of the disk, and so that needs to be fixed. But we can decide, if you're, in the first 75% of the disk, insert that at the front of the list, and if you're in the last 25% of the disk, insert that at the end of the list, and so that would, relatively easily balance the performance. And so, this came up, the performance problem with the MBAlloc came up not because of huge storage like we see in Lustre, but because of very slow flash devices used in embedded handsets. They actually found the same kind of problem because they had lots of erase blocks, and the optimized scan was allocating too widely across the disk, and so that was hurting the allocation performance. But so there's a few things that are in flight, but it's a problem that we're very interested to address, just because of these, the demand for such huge OSTs. And, it'll be, in one of the near upcoming releases, we'll have something to address these issues. So I think that's it. Any questions?
Thank you. Question?
About the MB stats, where you could see at what point you would need to do some tuning maybe. When do those reset?
The MB stats. Well, I can't say for sure. Obviously at boot, or remounting. I don't know if you can write into this one to reset them. And normally in the Lustre tunables you can. If you write anything into a Lustre tunable file, it will reset all of the counters, but I can't say for sure. But this would probably be from the time of boot.
All right, thanks.
Or mount, I should say.